Oh, lots of people at home. All right, people at home, can you hear me? Can you see the board? Yep. All right, let's get started. So, cyclohexanes. Cyclohexanes contain a little bit more information than we thought they did. We know there's a chair, and if we undergo 2 ring flips, then we get the other chair. And what happens then is that all my axial positions get converted into equatorial positions. And vice versa, all the equatorial positions get converted into axial. Okay. Do you remember K? The equilibrium constant, capital K? What did K equal? This goes forwards and backwards. It's completely reversible. These 2 conformers, these are conformational isomers or conformers, contraction. Value of K was the concentration of products divided by the concentration of reactants. And it turns out that when we look at equatorial turning into axial positions, there's a preference. So I'm going to write that the other way around. I'm going to have my product be the equatorial. Axial positions turning into equatorial positions. So my equatorial position is the numerator in this equation, not the denominator. For hydrogen in cyclohexane, that value is 1, meaning no preference. You put a halogen on this molecule, like a chlorine or a bromine. I didn't bring any numbers to class, but that number is now somewhere around 3. Meaning, the chlorine would rather be in the equatorial position 3 times more often than it would be in the axial. and that is a steric repulsion. Chlorines are big, much bigger than hydrogens, and their electrons repel in the eclipsed position. So they don't want to be axial, they would much rather be equatorial. When you turn that into a methyl, I think that number turns out to be something like 15. So it's not mass that's doing this, because an individual chlorine atom has a mass of 35.5. Well, 35 or 37, depending on which isotope it is. But the total mass of a methyl group is just the 12 for the carbon and the 3 hydrogens, so it's just a mass of 15. But it's taking up more space because it's got that tetrahedral blob on it. By the time this is a branched, actually I can't have that hydrogen. Is a branched alkyl group, like a little moiety, a group that we would call tertiary butyl. It's 4 carbons. Looks like this. And then this is attached to the ring. The ring goes here. Okay. The preference for this to be equatorial is 1600. So it's not going to go to the axial position, hardly at all. Okay. That is something we have to take into account when we're told I have ethyl cyclohexane. That ethyl group is going to demand to be in an equatorial position. And if you sketch it in an axial position, then you've probably sketched it wrong. How could that possibly matter? When these things end up being biochemicals, everything in biology depends on shape. And the shape of an axial substituent is not the same as an equatorial substituent. They have very, very different outcomes. Okay, all right, let's do a few and see what we can come up with. Yeah.
So you said the larger the number is going, that's like 1600, it almost never goes to equatorial.
Is going to be equatorial almost all the time, 1600 to 1. So this is reactant turning to product. So my product is my equatorial number. So this is how much I prefer being in an equatorial positions. Hydrogens are ambivalent. Heavy atoms have a preference. But once you start to get bulky, it really shoots through the roof. So this is a steric effect. It is because of size. It's not because of mass. Typical exam questions, quiz questions say, sketch the most stable conformer of, and then there's a name. Let's start with something simple. Sketch the most stable conformation of ethyl cyclohexane. So there are two shapes that we could use as the backbone of our molecule. It could be a chair or it could be a boat. It's not going to be the boat. It's going to be the chair. So draw a chair and then put an ethyl on it. Becca, the boat is the eclipsed form of the molecule, and the chair is the staggered. So there is less repulsion in the staggered form. And the staggered form is the chair. The boat is always higher energy. Thank you for reminding me, because we have to draw Newman projections today, and I had completely forgotten that we have to do that. Okay, so you should have a backbone that is a chair. We're going to need 12 substituents on this thing, 11 of which are hydrogens, and 1 is an ethyl group, C2H5. So first things first, I've got 6 carbons. Would any of these carbons lend themselves to displaying the molecule most accurately? If I put the substituent here, I'm going to see it better than if I put it in this one in the back. Don't ever put it in the one in the back. You're given free rein. You've got 6 carbons to stick a substituent on. Don't put it on one of the ones that you can't see properly. Put it on one of the ones that sits out. Okay, so all of these are hydrogens. Some of them are axial, some of them are equatorial. One of those 2 positions gets the ethyl, one of them gets the hydrogen. What goes here, where my finger is pointing? What goes there? Hydrogen. That molecule has an alkyl substituent, and it is going to want to be in the equatorial position. So go make it that way. Okay? All right, let's make some molecules.
When you write about the ethyl group, does it really matter whether you set parentheses around CH3? Is there a particular way that needs to be written?
I'm okay with you doing it anyway. You do it the way that you understand the best. Okay? The question was, do I have to write do I have to write the alkyl groups any particular way? This is as a condensed structure, but if you wrote the Kekulé structure out, fine. If you wrote the zigzag out, because hey, this is all zigzag, fine. Whatever works for you. If you wrote C2H5, fine. I want you to come to your best understanding. Okay. There is no one perfect way. The way that I say. Okay, let's take what we've got and modify it. Just going to move the name over a little bit. Here's a hexane. It's now a cyclohexane. There you go. And it's a chair. I'm going to add an ethyl to it. And when it's the only substituent, I don't have to give it a number because that automatically is carbon number 1 now. So this is our preferred form of ethyl cyclohexane with the ethyl group in the equatorial position. If I did the ring flip and moved this, oops, that way, this is now close. And of course, this is allowed to swing around, and now this is far too close, okay? This is too much repulsion. There are electrons in this bond, and there are electrons here. Those electrons are all repelling each other. So no thank you. Let's just have that. Now, at room temperature, this thing is wiggling and waggling all around, but it's going to spend more time doing this than it ever will doing that, okay? In the chemistry world, oxygen is red, but I don't have any greens. Halogens would be green. We're going to put a chlorine in this thing. We're going to put the chlorine at the 2. Go ahead and sketch it. This is carbon number 1. One of those 2 gets to be carbon number 2. No particular reason why you would do the one at the back or the one at the front. They're about the same. Pick one. Oh, people playing at home, I'm going to punish you. Use the whiteboard. If you have a tablet, you could sketch this with your finger or with a stylus. If you're doing this with your mouse, good luck. Somebody at home, draw me the most stable conformation of 2-chloro, 1-ethyl cyclohexane. That amuses me. It's funny. There is a clear, there you go. All right, deducting points for everybody playing at home for inadequate sketching. All right, here is a chair. My ethyl group is in an equatorial position where it can do no harm. That means we're going to add a halogen. We have two options. You'll see that we have two options. The halogen could go here, or it could go here. These need names. What should we call this one? Sam, Sam, and Mike. Sam and Mike. So football is back. For those of you that, if you get it, you get it. Sam, Mike. There's a poll. Sam, Mike. All right, I'm going to call it. Hurry up and vote. All right, I have a 8-2. 8-2 in favor of Sam. If you are one of those people in the big majority, defend your answer. Why this one? Come on, people playing at home. Defend your answer. People in the room, anybody who picked this in the room? Why?
Because if it's on the other one, it's capacity, so it's less speed.
Okay. That's a defense. So in the room, the defense is this is further away than that. And my question is it? The equatorial positions push outwards and away from each other. The axial positions, even if I can be away from that ethyl for a bit, I have these repulsions here. Remember what we said? It was on the board 10 minutes ago. Halogens have a preference to be in the equatorial position, about 3-to-1. This is the answer. Mike is the answer, not Sam. Sam's a terrible answer.
Thanks.
I wasn't actually looking at you, I was looking at the screen. People at home are not actually on the screen. No. This is the best answer. So we have to sketch this, and then we have to come up with another way of representing it, because after you see a couple of dozen of these drawn by students, you say, oh, please, just make this simple, because they're not clear. Okay, so our chlorine goes here. And I get both substituents being equatorial. Both substituents being equatorial. That's the best answer. If I put the chlorine up here, that chlorine would be axial, and the ethyl would be equatorial. Well, that's only half good. Okay, so this is my best answer. I'm going to show two different ways of sketching this. This is one way. And if it says draw the most stable conformer, this is a good way of showing it. If I drew the molecule as a hexagon, is the chlorine pointing towards me or away from me? See this hydrogen? That hydrogen is pointing towards you. That means that chlorine is pointing away. See this ethyl? Is that ethyl pointing towards you or away from you?
The first one. Second.
This bond is pointing towards you because there's an axial one behind it pointing away. When you go around, and we mentioned this last week, when you go around the ring, the equatorial positions alternate up, down, up, down, up, down as you go around the ring, as do the axial ones. If we were to look at the axial positions in this ring, up, down. Where am I? I've lost my way. It became a boat. Up, down, up, down, up, down. The axials alternate up and down. The equatorials, a little bit down, a little bit up, a little bit down, a little bit up, a little bit down, a little bit up. So knowing that I've got two groups next to each other and they're both equatorial, this is an alternate way of saying that. Now they're both equatorial and they're next to each other. If they're both equatorial and they're next to each other, one has to be up and one has to be down. One of them is on the front face of the molecule and the other one is on the back face of the molecule. This is the trans isomer. This is trans 2 chloro 1 ethyl cyclohexane. The cis isomer would be this. This is trans. This group is pointing away. That group is pointing towards you. If I put them so that they were both on the same face, this is on the front face of the ring. This is on the front face of the ring. This is now the cis isomer. We have the cis and trans isomers. This is the molecule that's shown on the board. If I flex this and rotate it, can I turn this trans isomer into the cis isomer? That's a yes/no question for those of you playing at home. Can I make the trans 2-chloro-1-ethyl cyclohexane become the cis 2-chloro-1-ethyl cyclohexane by doing a conformational change? No, no, exactly. To do the change from trans to cis, you have to take a bond off, physically move the atom, and then put it back on a new place. That is not a conformational change. That's a something else change. That's a configurational change, not a conformational change. Configuration is the attachment of the bonds. Conformation is how they wiggle around in 3D space. Okay. Do it again. Show me the most stable conformer of 1, 3 dimethyl cyclohexane. Oh, I still didn't do the Newman projections. Knock yourself out, people at home. Have a go. Okay, it's looking better.
Oh, gosh.
Okay, some interesting stuff on the board there. When you just show me the hexagon with the wedges or the hatch lines, what it fails to tell me that I am interested in is, are you showing me a boat or a chair? Okay, so those answers are good enough for people who already know it's never going to be a boat. But for people who don't know it's never going to be a boat, drawing the hexagon with the wedges and hatch lines is not enough. Okay? I think you all did a fabulous job. Now let's look at the real answer. It's a chair. I have to pick position number 1 and position number 3. And I need to do it so that I don't pick anything at the back right here. Putting a substituent here and here. Okay, I should be able to see that. If this is number 1, number 2, and number 3, you should be able to see that as well. If that's number 1 and number 2 and number 3, or 1 and 2 and 3, I could get away with that. Just don't put anything in this back corner right here. That was the difficult one to take a look at. Okay. There you go. 1, 2, 3, 4, 5, 6. Going clockwise from the top right. I need 2 methyls. One of the methyls goes on carbon number 1. Does it go here or here? Scream real loud when I touch the place that you want it.
Wow.
Going to skip over carbon number 2. Here's carbon number 3. Does it go here or here? All right. Everything else is a hydrogen. I have 2 methyls, both equatorial. Both equatorial. Cyclohexanes have the possibility of throwing up isomers that are either cis or trans. Cis isomers are on the same base. Trans isomers have the substituents on opposing faces. The most stable conformer of 1,3-dimethylcyclohexane. Is that the cis isomer or the trans isomer? Let's identify the substituents. These are my substituents. I have two methyls. If they're both pointing in the same direction, they're both on the same face of the molecule. If they're pointing in different directions, they're on opposite faces of the molecule. Cis is for the same, trans is for the opposite. What have I got, cis or trans? This is cis because they're both pointing down. Those are my axial hydrogens, which are obvious to see that they're definitely pointing up on carbon 1 and carbon 3, okay? That means that the equatorials have to be pointing down a little bit. Marcella asks a very, very important question. Is cis more stable than trans? And the answer is, it depends. I'm going to show you, because the previous one was trans. The previous best answer was trans. This best answer is cis. Maybe the next one, well, there's only two possible answers, is one of the others. So, Marcella, it depends, and hopefully we're going to figure out what that depend is. Hold on a couple of minutes. So these are both on the same side, same face. That's the cis isomer. So draw the most stable conformation of 1,3-dimethyl cyclohexane. That gets to be the cis. Okay, I write in all caps all the time. Dimethyl cyclohexane is all one word. None of our chemicals are proper nouns, so we don't capitalize anything in the name. The hyphen, the numbers with the comma in between, and then the cis out front. If you're typing this up, that's in italics. If you can't write in italics, you are allowed to underline it. This is lowercase, either underlined or in italics, then the number, and then all lowercase regular text. Should I figure it out?
Thank you. Okay. I just typed it. There we go.
Question is, draw the most stable conformer of trans. 1 butyl, 3 methyl, cyclohexane. It's a chair. And it has substituents at the 1 and the 3. They are trans to one another. And at the 1 and 3 positions, the axials are cis to one another, and the equatorials are cis to one another. So in this case, for a trans molecule, one of the substituents will be pointing up in an axial arrangement, and one will be pointing down in an equatorial arrangement. Put the butyl on 1. Does the butyl go here or here? Here or there? Here, there.
There. Like.
Okay. At position number 3, does the methyl go here or go there? Told you in the question, these two groups have to be on opposite sides, opposite faces of the molecule. They're trans, to be on opposite faces. So if this substituent is pointing down, that leaves me no option but to put the methyl pointing up on 1, 3. But remember, methyls don't want to be in an axial position. Methyls want to be in an equatorial position. But butyls demand to be in an equatorial position. Ethyls want to be in an equatorial position. Butyls are going to require it. So you have 2 different substituents. The one that is the biggest, bulkiest one is the one that is going to determine what everything else in the ring does. If you are told that this has a butyl and a methyl, and they're on the 1 and the 3, and they are trans to each other, that means that the butyl must be equatorial. And because it's a trans isomer, that means that the methyl and the ethyl have to be on opposite faces. This one is down, that one is up. That methyl has no option. Has to go axial. Has to go axial. Yeah.
Okay, so if it was the trans 1 butyl, but then it was 2 methyl cyclohexane, then would you put on the second one but make it also equatorial so that it's facing?
Okay, question in the room about a slight change to the molecule. What's your new name?
It was trans and then 1 butyl, 2 methyl cyclohexane.
Trans 1.
And then
So we named the lowercase one first, and the lower in the alphabet. B is lower in the alphabet than M, so you name the B first. Let's put the butyl at 1. And 2, ethyl.
Did you see that in
Okay.
Just, I wanted to know.
Because it's like she's,
This is now 1, 2. This is getting to the question that Marcella asked earlier. Is cis better than trans? Is trans better than cis? It depends. It depends. The trans isomer at a 1, 2 let's make this number 1 and that number 2, or this number 1 and that number 2, okay? So I can put my butyl here and, oops, and it be equatorial. It is pointing down. When I look at the 2, my equatorial points a little bit up, and my axial points down. So the trans isomer, when the 1, 3 is axial and equatorial, but when it's 1, 2, they both get to be equatorial. So when Marcella asked earlier on, is trans better than cis? Is cis better than trans? It depends. It depends on what the gap between the positions is. If it's 1, 2, remember, the axial positions alternate as you go around the ring. Up, down, up, down, up, down, up. Things the equatorials also do. So you can have trans be the best for a 1, 2. Cis would be the best for the 1, 3. Trans would be the worst for the 1, 3. Am I out of time? Oh, I did. So, Becca, Monday. Remind me about Newman projections. We didn't get to it. They're ugly for cyclohexanes, but we've got to get to it. All right, everybody have a good weekend. I'm going to do a couple of small changes to Blackboard. You're going to see some assignments come your way. Okay.
right?
Which one?
No, right? Like, also, we have a due date for lab 2 next week, but like.
Yes, actually, I've been told that. I'll have a look.
Wednesday, it's gonna be very hard to bring Blackboard.
Homework due Wednesday, September the 11th. Homework 2, let's have, well, we can have that be done next Wednesday, which is what, the 15th? Something like that. 16th maybe.
Thank you, Dr. Lamar.
All right, yeah, I'm going to move a few things around at Blackboard.
Yes, sir.
You'll get plenty of notification when something important changes.